We'll start with our study of structural engineering by identifying the types of structural supports which determine how a structure behaves to support externally applied loads. So this first support is a pin or hinge, and suppose this body is loaded, then this will produce reactions in the vertical and horizontal direction to resist translation, and effectively the horizontal and vertical displacements at the pin are zero, but the pin allows rotation. So therefore translation is fixed, but rotation is permitted by the hinge. Now this type of support is a rigid or fixed support which produces reactions in both the vertical and horizontal direction, as well as a moment reaction to enable a structure to resist an applied load. So in this case, before and after this structure is loaded, there's no translation permitted in the horizontal and vertical direction, and the fixed support also does not permit rotation. So effectively, the beam in this case remains at 90 degrees before and after it deforms. Now in this third case, we have a rigid roller support, and when this beam's loaded, it'll deform something like this, because the rigid roller has a horizontal reaction which prevents translation in the horizontal direction, but it has no reaction in the vertical direction. So therefore the beam can translate at this support vertically. And because this support produces a moment reaction, then there's no rotation permitted at the support. So in other words, before and after deformation, the beam remains at right angles at this point to the support. Now we can use these supports to model parts of a structure. So for example, if we want to model this horizontal beam of this cable-stayed bridge, well, this tower here takes very large compression loads, so we can model the beam as sitting on a roller that does not translate up and down. So effectively this roller has a vertical reaction that does not permit translation in the vertical direction, but it permits translation in the horizontal direction. And similar to a pin, this roller also permits rotation. Now given that this beam is also supported by cables which take tensile loads, well, at this point the cables are going to allow the beam to translate up and down. So therefore in the vertical direction, translation is allowed. So here we model this support as a flexible roller, which has a certain stiffness and produces a reaction in the vertical direction that enables translation, but is limited by this stiffness K. Structural elements develop internal forces to resist external loads imposed on them. And the first example is a beam, which develops internal shear forces and bending moments to resist an external load via bending, and the load's applied transversely to the beam. Now truss elements resist external loads via compression or tension in their members. Now cable elements only resist tensile loads, so they develop tensile forces internally. And columns typically resist compression loads, and they can also resist lateral loads, such as wind loads, via bending. So they can also develop internal shear forces and bending moments. So in this case, where they resist bending and compression at the same time, they're called beam columns. And here are examples of columns. So this huge tower in a cable-stayed bridge, and here you have cables which are tension members, and you have a beam here resisting transverse loads that may be applied from a vehicle. Common structures are assembled from the typical structural elements, and they transfer loads through those elements. So for example, this arch bridge can be simplified as a 2D model, and the arch members consist of beam columns that take bending and compression, whereas the cable elements take tension and they support the beam, which supports loads in bending. Now the cable-stayed bridge also consists of a beam which develops bending loads, and the cables also support the beam through tensile loads, and the tower can be modelled as a column which takes compression loads, and these loads are ultimately transferred to the supports or the foundation. Now trusses in general consist of a top chord and a bottom chord, and these are the bracing members, and this member here is the vertical strut if it takes compression, or tie if it takes tension. So truss members are generally struts or ties that take only compression or tension. Now moment frames consist of beams and columns that are rigidly connected together. So before and after deformation, these remain at right angles at these nodes. And the beams transfer loads by bending, and the columns, which are generally beam columns because they transfer lateral loads via bending and axial loads via compression or tension. Let's find the reactions for this cantilever, which is a beam that's fixed at one end. So we'll take a free body of the cantilever and draw all the forces acting on it. So we have a 3 kN force at the tip, a vertical reaction at the fixed support, and also a horizontal reaction, and a moment reaction to prevent rotation. And now applying Newton's first law in the horizontal direction, where the sum of forces are equal to 0, and we'll take forces acting to the right as positive. So therefore AX is 0. And now we'll take a sum of forces in the vertical direction, where the net force is 0, and we'll take forces acting upwards as positive. Therefore AY minus 3 kilonewtons is 0. So AY is 3 kilonewtons. And now we'll take a sum of moments about A, and that's equal to 0, and we'll take anti-clockwise as positive. So the line of action of these reactions passes through this point, so they produce no moment or torque. And therefore we have MA anti-clockwise minus 3 kilonewtons by the perpendicular lever arm. So the force at the tip produces a clockwise moment about this point, and that's equal to 0. So therefore MA is 6 kilonewton meters. Let's find the reactions for this simply supported beam. Well, at the pin we have vertical and horizontal reactions, And at the roller we have only a vertical reaction. Acting on this beam which we took as a free body. Now we can resolve the oblique force into horizontal and vertical components. So using trigonometry, this would be 3 cosine 60 degrees, and the vertical component is 3 sine 60 degrees. And I'll draw the special trig triangle for your reference. Now we can find the horizontal reaction by taking force equilibrium in the horizontal direction. So we have AX minus 3 cosine 60 degrees is equal to 0, and cosine 60 is 1/2 using the special trig triangle. So AX is equal to 3 by 1/2, or 1.5 kilonewtons. Now next we'll take moments about either support, because taking a vertical force equilibrium will give us two unknowns. So I'm going to take moments about support A. And counterclockwise moments are positive. So we have reaction By by the moment arm, which is 2 meters, and then minus the distributed load, which is 1 kilonewton per meter, multiplied by 1 meter, which gives us the resultant force acting in the middle. And this force has a moment arm of 0.5 meters from the support, and produces a clockwise moment, so it's negative. Now the horizontal component of the oblique force produces a counterclockwise moment about A. So 3 cosine 60 is 3 by 1/2, and then multiplied by the moment arm, which is 0.3 meters. And the vertical component produces a clockwise moment about A, and sine 60 degrees is √3/2. And the perpendicular moment arm is 1.5 meters. And that's all equal to 0. And solving this equation for reaction By, you'll obtain 1.97 kilonewtons. And now we can take a sum of forces in the vertical direction, with upwards being positive, to find our reaction AY. So we have AY minus the magnitude of the resultant of this uniformly distributed load, and minus 3 sine 60 degrees, which is 3√3/2, and plus the reaction By, which we just found. And that's all equal to 0. And now we can solve for the reaction AY, and that gives 1.63 kilonewtons. Let's find the reactions for this simply supported truss. We'll take in a free body of the truss and identifying the reactions that are acting on it. So at node A, we have a vertical reaction and a horizontal reaction. And at the roller, we only have a vertical reaction. And firstly, we can take a sum of moments about node A to eliminate those reactions, with counterclockwise being positive. So we have By multiplied by the moment arm, which is 2 meters, minus 1 kilonewton, multiplied by the moment arm, which is 1 meter, given the geometry of this right triangle, and minus 2 kilonewtons, multiplied by the moment arm of 1 meter. And that's all equal to 0. And solving for reaction By, we obtain 1.5 kilonewtons. And now we can take a vertical sum of forces. So that's equal to 0, with upwards being positive, to find AY. So we add By and minus 2 kilonewtons. Therefore AY is 0.5 kilonewtons. And if we take a horizontal equilibrium of forces, where forces pointing to the right are positive, we have AX plus 1 kilonewton is 0. So therefore we obtain AX is minus 1 kilonewton. And because our answer is negative, AX is actually pointing to the left, as you would have guessed, to counteract this horizontal force. So therefore, if we draw it pointing to the left, we can take this as a positive value. The method of joints is useful for finding all member forces in a truss, and is best illustrated with an example. And first you find the reactions, and then take an equilibrium of the joints strategically to first identify the zero force members. So the member forces going through joint D are in member DF and BD. And you can verify by horizontal and vertical force equilibrium that these forces are zero. And similarly, if we take equilibrium of joint E, we have the forces in member AE and BE, and a vertical force in member EF going through that joint. And by vertical equilibrium of forces, we can observe that the force in member EF is 0. And similarly, if we take an equilibrium of joint C, we have an externally applied load of 1 kilonewton going through that joint, and therefore the force in member CF, I'm going to guess, is pointing to the left, to put that force in equilibrium. And we have a force in member AC acting downwards. So therefore a vertical equilibrium of forces tells us that member AC is also a zero force member. And now I'm going to take an equilibrium of joint B. So we have a force of 1.5 kilonewtons going through that joint, which is the reaction. I'm guessing that the force in member BF must act in this direction, because it must have a vertical component that puts that reaction in equilibrium. And this angle here is 45 degrees. And therefore, because this force acts to the right, the force in member BE must act to the left to put that force in equilibrium. And now if we take a vertical force equilibrium with the positive forces acting upwards, then we have 1.5 kilonewtons minus FBF sine 45 degrees, and that's equal to 0. And sine 45 is 1 on root 2. So therefore FBF is 1.5 root 2 kilonewtons, which will write up here. And because this force is going into the joint B, then this member is in compression. And now if we take a horizontal equilibrium of forces, with positive to the right, we have FBF, which is 1.5 root 2, cosine 45 degrees, which is 1 on root 2, minus FBE is equal to 0. And here we have a cancellation, so FBE is 1.5 kilonewtons, which will write over here. And because this force is pulling away from joint B, then this member is in tension. And now if we take a horizontal equilibrium of joint E, using a consistent sign convention, then we have FBE, which is 1.5 kilonewtons, minus FAE is 0. So therefore FAE is also 1.5 kilonewtons, which we'll again write over here. And because this member is pulling away from joint E, then this here is a tension member. And if we take a horizontal equilibrium of joint C, using the same sign convention, we have minus FCF plus 1 kilonewton is 0, and therefore FCF is 1 kilonewton. So we'll write that opposite the member. And this force is going into joint C, so this member is in compression. And now if we take an equilibrium of joint A, we have the reaction forces of 1 kilonewton and the vertical reaction of 0.5 kilonewtons. And we also found FAE, which is 1.5 kilonewtons. So therefore the force in member AF must be acting in this direction. To put the 0.5 kilonewton reaction in vertical force equilibrium. And now if we take a vertical force equilibrium of this joint, with upwards being positive, we have minus FAF sine 45 degrees, which gives the vertical component, plus the 0.5 kilonewton reaction is equal to 0. So therefore if you solve for this force, we get FAF is 0.5 root 2 kilonewtons, where sine 45 degrees is 1 on root 2. And we'll write this force over here. And because the force is going into joint A, this member is in compression. So try to visualize how this truss would deform, and the compression and tension will make more sense. The method of sections is used to find the forces in specific members of a truss. So to find the forces in these three members, we take a section through those members. So what I'll do is cut this part of the truss out and analyze it over here. And we'll draw in a geometry for completeness. So by taking a free body off the right hand side of the truss, we've exposed the internal forces in the members. So I'm guessing that this force in member BF is acting down and to the right to counteract this reaction, and therefore the force in member BE I'm guessing will act to the left, because we know that this force in member DF is a zero force member, but we'll verify this anyway. Now we need to be strategic of which equilibrium equation we're going to use. So what I'll do is take a sum of moments about node B, and that's equal to 0, with anti-clockwise being positive by our convention. Well, we can see that the force in member BF and BE and the reaction pass through this joint. So that verifies that the force in member DF is 0. And now if we take a vertical force equilibrium with upwards positive, and we know this angle in the truss is 45 degrees, then we have minus FBF sine 45 degrees to get the vertical component, which is 1 on root 2, plus the 1.5 kilonewton reaction is equal to 0. So that gives FBF is 1.5 root 2, and because it's compressing the member, this member is in compression. And now we can take a horizontal equilibrium of forces, with positive being to the right. So we have minus FBE plus FBF, which is 1.5 root 2, by cosine 45 degrees to get the horizontal component, which is 1 on root 2, and that's equal to 0. So therefore the force in member BE is 1.5 kilonewtons. And because this force is pulling on the member, this is a tensile force. We're asked to find the forces in members CE and CG, so that's where we'll take our section through the truss. So I'm going to cut this part of the truss out and take a free body of it and draw in the remaining geometry to get a better visual. So this was node E, and over here we'll just call this the node CG. And we'll extend this dimension of 2 meters. And by cutting the truss, we've exposed the forces in these members. So because this force is a horizontal component, I'm going to guess that this member CG is being compressed. And because we've got an upward reaction at node A, the force in this member must be acting downwards to put that vertical reaction in equilibrium. And because this force is a vertical component, that's going to push the truss downwards, and I'm going to guess that this member AE is in tension. And now we need to be strategic on which equilibrium equation to use to find the forces in these members. So if I take a sum of moments about node E, with anti-clockwise being positive, well, we can see that the lines of action of all the forces pass through these nodes, except the vertical reaction and FCG. So what we have is the vertical reaction is root 3 multiplied by the moment arm, and that causes a clockwise moment about this node. And then we have the force in member CG, and using the special trig triangle, if this dimension's a meter and this angle is 60 degrees, then this dimension's root 3, which is the moment arm. So therefore the force in member CG is 2 kilonewtons. And a positive result means we got the direction right, so therefore this member is in compression. And now if we take a vertical sum of forces, with upwards being positive, we have the vertical reaction minus the vertical component of force CE. So that will be FCE sine of 60 degrees. And sine of 60 degrees is root 3 on 2 using our special trig triangle. So therefore FCE is also 2 kilonewtons. And because that's pulling away from the member, this member is in tension. To determine if a truss is stable, we can first check that it's determinate, meaning that the number of equilibrium equations is equal to the number of unknowns. And the unknowns are the forces in each member and also the reaction forces. So the number of equilibrium equations is equal to the number of joints multiplied by 2 equilibrium equations per joint, being the sum of forces in the horizontal and vertical direction. So for this truss, we have 4 joints by 2 equilibrium equations, which gives 8 equations. And a number of unknowns are the member forces. So here we have 5 members plus 3 reactions, being 2 at the pin and 1 at the roller, which equals 8. And therefore the number of equilibrium equations is equal to those of the unknowns, and consequently this truss is stable. Now for this truss over here, we also have the same number of reactions, being 3, and the same number of members, being 5. So the number of unknowns is the same. And we also have 4 joints, so also add equilibrium equations. But this truss is not stable, because if we take moments about this point here, using anti-clockwise as positive, we have this external force by the moment arm, being the distance to this joint, must be equal to 0. But because this force and lever arm are both not 0, then this equation is not satisfied. And therefore the reactions are not going to be able to resist a torque that's generated about this point. And this truss is consequently unstable. Now for this truss here, we have 2 unknown reactions. So the number of unknowns is 2 reactions plus 5 member forces, which gives 7 unknowns. And the number of equilibrium equations is the number of joints being 4 by 2 equilibrium equations per joint, which gives 8. And because the number of equilibrium equations is greater than the number of unknowns, then the system is overdetermined and this truss is unstable. So as you can imagine, because these rollers don't provide resistance in the horizontal direction, then this force is just going to push that truss and it's going to behave like a rigid body. A beam resists loads that are perpendicular to its axes via bending. And if we take a section out of the beam, which has a width delta x, we expose the internal actions, being the shear forces and bending moments. So on the other side, we have a shear force V plus delta V, and a bending moment M plus delta M. And now if we take a vertical equilibrium of forces, where upwards is positive, we have the shear force on the left minus the shear force on the right, and then minus the resultant of the distributed load. In doing some simplifications and solving for delta V, we obtain delta V is minus W delta X. And dividing through by delta X gives delta V on delta X is equal to minus W. Now in the limit, as delta X goes to 0, we obtain the following equation, which relates the derivative of the shear force with respect to X to the externally applied load. Now if we take a sum of moments about the right hand side of the section, with anti-clockwise being positive, we have a clockwise moment M plus the anti-clockwise moment M plus delta M, and the shear force produces a clockwise moment, so it will be minus V by the moment arm, and a uniformly distributed load has a resultant of W by delta X, and then multiplying by the moment arm of delta X on 2, and that's all equal to 0. And now we cancel out the m's, and we can also divide through by delta X. And this gives delta M on delta X is equal to V minus W by delta X on 2. And then if we take the limit as delta X goes to 0, this term drops out, and we obtain the following equation, which relates the derivative of the bending moment with respect to X to the shear force. And if we differentiate this expression, we get the second derivative of the bending moment with respect to x is equal to the derivative of the shear force with respect to x, which is minus of the uniformly distributed load. Depending on where you choose to cut a section out of the beam, you will observe jumps in the shear force and bending moment diagrams. So for example, if we have a point load on this cut section, which has a shear force V and bending moment M on one side, and V plus delta V, and M plus delta M on the other side. And taking a vertical equilibrium of forces, with upwards being positive, we have the shear force on one side minus the shear force on the other side, and minus a point load is equal to 0. In cancelling the V's, we obtain delta V is equal to minus P. And in the limit, we obtain dV is minus P, which means there's a discontinuity in the shear force on both sides of the point load, which is equal to the negative of the point load. Now similarly, if we look at a section that we cut around a couple, well, they're going to be exposed to shear force on both sides, and the bending moments on both sides. And this time, if we take an equilibrium of moments about the right hand side of the section, with anti-clockwise being positive, and we have minus M plus the bending moment on the other side, which is M plus delta M, and minus M naught, and minus the shear force V by the moment arm delta X, and that's equal to 0. And here M cancels, so solving for delta M, we obtain M naught plus V delta X. And in the limit, as delta X approaches 0, this term drops out, so we obtain dm is equal to M naught. And similar to the shear force, we have a discontinuity in the bending moment on both sides of that couple, and that jump is equal to M naught. When a beam sags, fibers in the bottom of a section that we take from it are stretched, and the upper fibers are compressed. So this deformation is caused by the sagging moments. And on the right hand side, when a beam such as a cantilever is loaded in this manner, then you get tension in the top of this section that we take from it, and the fibers in the bottom of the section get compressed. And that's due to the hogging moment. So for the positive sign convention, we have sagging moments and positive shear forces acting in this manner on left and right of the section. And here we have the hogging or negative sign convention, where a shear force acting downwards on the left of a cut section is negative, and on the right of the cut section the shear force is negative upwards. And for example, if you had a concrete beam, cracks develop in tension, so you'd put your reinforcement in the bottom of that beam to prevent that crack from propagating. And given concrete's weak in tension, when you have hogging moments, the crack will develop from the top, so you'd put your reinforcement in the top of the beam to prevent that crack from propagating. Let's draw the shear force and bending moment diagrams for this beam. So what I'm going to do is take a free body of a section that's at some distance x from the support. So therefore the length of the section is 3 minus x. So the 2 kN force acts on this section, in addition to the internal shear force and bending moment. And note that by our positive sign convention, we have the shear forces acting in this direction, and we have sagging moments acting as follows. So therefore, because we expose the shear force and bending moment on the left, we start with this sign convention. And now if we take an equilibrium of forces in the vertical direction for this cut section, we have the shear force minus 2 kilonewtons is 0, and therefore the shear force is constant at 2 kilonewtons. And now if we take a sum of moments about the left point of that cut section, with counterclockwise being positive, we have minus m minus 2 kilonewtons by the moment arm, which is 3 minus x, and that's equal to 0. So therefore we can write the bending moment as minus 2 by 3 minus x, which is the same thing as 2 by x minus 3. And now we'll draw the shear force diagram. So the shear force is positive at 2 kilonewtons and constant, so it looks something like this. And we draw the positive shear force diagram at the top of the beam. And now drawing the bending moment diagram, at x equals 3 meters, we have a 0 bending moment, and at x equals 0 meters, we have minus 6 kilonewton meters. And the bending moment diagram varies linearly, so it looks something like this. And note that we draw hogging moments, which are negative, at the top of the beam, and positive sagging moments on the bottom of the beam. Because remember that when a beam hogs, you get tension in the top of the beam, and that's where we'd put our reinforcement in a concrete beam. Let's draw the shear force and bending moment diagrams for this beam. So at a fixed support, there's force and moment reactions, but since there's no forces acting on the beam and only a couple, then there must be a moment reaction that counteracts that couple. And now if we take a free body of a section that's at a distance x from the support and expose the internal shear force and bending moment, then from x equals 0 to 1 meter, if we take an equilibrium of forces, then the shear force is 0. And if we take an equilibrium of moments about the rightmost point of this cut section, then we see that the bending moment is constant at 2 kilonewton meters. Now conversely, if we take the cut section at some distance x from the support and expose the internal shear force and bending moment, well, the moment reaction is going to act on this section, and the externally applied couple is also going to act on this section. So from x equals 1 meter to 2 meters, taking an equilibrium of forces gives the shear force is equal to 0, and taking an equilibrium of moments about the rightmost point of that section, with anti-clockwise being positive by our convention, then we have minus 2 kilonewton meters plus 2 kilonewton meters plus m is 0. So therefore the bending moment is 0 between x equals 1 and 2 meters. And drawing the shear force diagram, well, that's just going to be 0 kilonewtons across the entire beam. And if we draw the bending moment diagram, from x equals 0 to 1 meter, we have a constant bending moment, which has a magnitude of 2 kilonewton meters. And from x equals 1 meter to 2 meters, the bending moment is 0. And if you recall our sign convention, sagging moments are positive by this convention. Let's draw the shear force and bending moment diagram for this beam. So first we'll take a free body diagram of the beam and draw in the reactions. So at the pin we have a vertical reaction and a horizontal reaction. And at the roller we have a vertical reaction. And taking an equilibrium of moments about the roller with our counterclockwise convention, we have a clockwise moment produced by reaction A multiplied by the moment arm, and then a clockwise moment induced by the external load by the moment arm, and that's all equal to 0. And therefore, solving for AY, we obtain 6 on 4 or 1.5 kilonewtons. And an equilibrium of forces in the vertical direction, with upwards being positive, gives AY minus 2 kilonewtons plus our unknown reaction BY is 0. So therefore BY is 0.5 kilonewtons. And we know that AX is 0 by a horizontal equilibrium of forces. And now if we cut the beam, taking a free body of a section that's at some distance x from the pin, we expose the internal shear force and bending moment. So from 0 to 1 meter, if we take an equilibrium of forces with our upwards positive convention, the shear force is equal to the reaction AY, which is constant at 1.5 kilonewtons. And then taking an equilibrium of moments about the right point of that cut section, with our anti-clockwise convention, we have M minus the reaction AY by the moment arm is 0. So therefore M is positive 1.5x. And now if we cut out another section that's at some distance x from the pin, but this time the cut is after the external force. So on this free body we have 2 kilonewtons acting. The reaction AY, which is 1.5 kilonewtons, and an exposed internal shear force and bending moment. So from 1 meter to 4 meters, taking an equilibrium of forces with our usual positive convention, we have the shear force plus 1.5 kilonewtons minus 2 is 0. So solving this, we get the shear force is minus 0.5 kilonewtons. And I've taken an equilibrium of moments about the right handmost point of that section, with anti-clockwise being positive. We have M minus 1.5x plus 2 kilonewtons by this moment arm here, which is equal to x minus 1 meter, and that's equal to 0. So if you solve for M, we get minus 0.5x plus 2. And now we can draw in our shear force diagram, which is 1.5 kilonewton from 0 to 1 meter, and minus 0.5 kilonewtons thereafter. So as you can see, the jump here is equal in magnitude to the externally applied load. And now if we draw the bending moment diagram, from 0 to 1 meter, we have 1.5x. So 1.5 by 1 is 1.5 kilonewton meters at the point load. And similarly, if we substitute x equals 1 meter here, we get 1.5 kilonewton meters also. So the bending moment diagram is piecewise continuous. And now at x equals 4 meters, the bending moment is 0. And we can see that by these two equations, the bending moment diagram is piecewise linear. So this makes sense because a pin and roller do not resist rotations. Let's draw the shear force and bending moment diagram for this simply supported beam under a uniformly distributed load. Now we can apply vertical equilibrium of forces to find the reactions. We'll recognize that the resultant force acts in the middle by symmetry, and that's equal to WL, and therefore the reactions are WL on 2 by symmetry. And now we can take a free body of the section that's at some distance x from the support, thereby exposing the shear force and bending moment. And taking this section anywhere along the beam gives the same forces acting on it. So if we take a vertical equilibrium of forces on that section, with upwards being positive, then we have WL on 2 minus W by the distance x minus the shear force is equal to 0. So therefore the shear force is WL on 2 minus Wx. Now taking an equilibrium of moments about the rightmost point of the section, with anti-clockwise being positive, we have minus WL on 2 by the moment arm, which is a clockwise moment, and then plus Wx, which is the resultant of the uniformly distributed load acting in the middle of that cut section, and by the moment arm, which is x on 2. And plus m is equal to 0. So therefore the equation for the bending moment is WL on 2 by x minus Wx squared on 2. And now we can draw the shear force diagram. So we have a jump in the shear force at x equals 0, which is equal to that reaction. And at x equals L on 2, the shear force is 0, and we can see that the shear force is linear along that beam. So at x equals L, the shear force is minus WL on 2, which is again equal to the magnitude of the reaction at the other end. And now we can draw the bending moment diagram. And we know that at a pin and a roller, the bending moment is 0. So if you substitute x equals 0 and x equals L, that's what you'll get. And remember this equation that says that the derivative of the bending moment is equal to the shear force. So therefore if we set the shear force to 0, we obtain WL on 2 minus Wx, and therefore x equals L on 2. And therefore the bending moment is a maximum so if we substitute x equals L on 2 for the bending moment, we obtain m of L on 2 is equal to WL on 2 by L on 2, which is WL squared on 4, minus WL squared on 8. And therefore, the maximum bending moment is WL squared on 8 and occurs at midspan. And because of the x squared term, the distribution of the bending moment is parabolic. So it looks something like this. With a maximum of WL squared on 8. Let's draw the shear force and bending moment diagram for this beam with an overhang. And first we'll identify the reactions. So at the pin and roller, we're only going to have vertical reactions, because there's no horizontal forces acting on the beam, and therefore the horizontal reaction at the pin is 0. And if we take moments about support A, with anti-clockwise being positive, then we have a clockwise moment produced by the 2 kN force with a moment arm of 1 meter. And we have an anti-clockwise moment produced by the reaction at B by the moment arm of 2 meters. And then we have a resultant force for that uniformly distributed load of 3 kN per meter by 1 meter. And that has a moment arm from support A of 2.5 meters. And that's all equal to 0. And solving for the reaction B, we obtain 4.75 kilonewtons. And if we take a vertical equilibrium of forces, with upwards being positive, we have AY plus the reaction BY minus 2 kilonewtons and minus the resultant from the uniformly distributed load. And that's all equal to 0. So therefore AY is 0.25 kilonewtons. And now we can draw the shear force diagram by simply following the forces on the beam. So we have AY being 0.25 kilonewtons, and because we only have a point load acting on this portion of the beam, the shear force diagram is constant here, and then we have a jump of 2 kilonewtons. So the shear force here is 1.75 kilonewtons. And again, the shear force diagram is constant. Then we have a jump in the shear force diagram equal to the reaction By at the support, and therefore the shear force is 3 kilonewtons here. And because we have a uniformly distributed load, the shear force diagram is linear and down to 0 at the free end. And we can draw the bending moment diagram in a similar way. So we have AY is 0.25 kilonewtons, and we can see that the moment along this portion of the beam here is simply that reaction force by the moment arm X. The moment arm is 1 meter, so the bending moment diagram here will be 0.25 kilonewtons by 1 meter. And on the right hand side, if we cut the beam from right to left, we have the bending moment and shear force exposed. And once you get to the support, the bending moment is going to be 3 kilonewton per meter, while 1 meter gives the resultant, which acts in the middle of the beam, and then multiply by the moment arm, which is 1 meter on 2. So therefore the bending moment here is 1.5 kilonewton meters. And because we have a uniformly distributed load, the bending moment diagram is parabolic and 0 at the free end. And on this portion of the beam, we're going to have a point load acting, so the bending moment diagram is linear. And because there's no externally applied couples, so for example if we had an externally applied moment here at the support, the bending moment diagram is piecewise continuous. The method of superposition can simplify plotting the bending moment diagram for a beam subjected to multiple different loads. So here we superimpose two cases where the beam is subjected to the point load and the uniformly distributed load. And if we look at this case, if you cut the beam from right to left, you can see that the shear force and the bending moment on the overhang is 0. So therefore this beam effectively behaves like a simply supported beam, and the reactions here are 1 kilonewton each by symmetry. So therefore, because of the point load, the bending moment diagram is piecewise linear, and the maximum bending moment is simply 1 kilonewton by the moment arm of 1 meter. And this bending moment diagram for a simply supported beam is well known, so it's equal to the point load by the span on 4. Now in the second case, if you cut the beam from right to left, you'll see that the bending moment at the support here is the uniformly distributed load by the length, which gives the resultant, which acts in the middle of the uniformly distributed load. So therefore the moment arm is the length on 2. So in this case here, the bending moment is 3 kilonewton per meter by the length gives the resultant, by the length on 2 gives the bending moment at the support. And because of the uniformly distributed load, the bending moment diagram is parabolic. So here it's 1.5 kilonewton meters. And because there's no load applied on a simply supported span, the bending moment diagram is linear. And there's no externally applied moment at the support, so the bending moment diagram is piecewise continuous. Now by the linearity of the bending moment diagram, at 1 meter, the bending moment is half of 1.5. So here is 0.75 kilonewton meters. And these moments here are negative because they're hogging moments. And if we superimpose these two cases, at the point load, we have a bending moment of 1 minus 0.75, which is 0.25 kilonewton meters. And at the roller, we have 0 minus 1.5, so that will be minus 1.5 kilonewton meters. And we can see that the bending moment is piecewise linear here when we superimpose these two bending moment diagrams. And then the bending moment diagram is parabolic on the overhang, so it looks something like this. We can draw the shear force diagram from a bending moment diagram. So what we do is cut two segments of the beam just after and before the support, and just after the support here, and take a free body of those segments. Well, we know that at a pin there's going to be a shear force which we assume points upwards by our initial positive convention, which I'll draw here for your reference. And at a pin we have 0 bending moment, and we'll call this shear force A. And at the roller we take this side of the convention, so we assume the shear force acts downwards, and here we have a hogging moment, and as we know, hogging moments cause tension on the top of the beam, and this hogging moment has a magnitude of 1.5 kilonewton meters. So on this 2 meter long segment there's also a point load of 2 kilonewtons acting on it. Now on this segment we also have a shear force, so I'll call this one VB1 and this shear force VB2. And we have a hogging moment which is negative, so it causes tension in the top of the beam. And that's the same hogging moment of 1.5 kilonewton meters. And at the overhang we have a 0 shear force and 0 bending moment. And this segment also has a uniformly distributed load acting on it, which has a magnitude of 3 kN per meter. And the segment has a length of 1 meter. Now if we take equilibrium of the first segment, so we'll take moments about support B, with anti-clockwise being positive, so that gives minus shear force A by the moment arm of 2 meters, plus 2 kilonewtons by the moment arm of 1 meter, and then minus the hogging moment, and that's equal to 0. So the shear force at A is equal to 0.25 kilonewtons. And a positive shear force diagram is drawn on the top of the beam. And here we know the shear force is constant because there's a point load acting on this segment. And if you take a vertical equilibrium of forces for this first segment, with upwards being positive, we have the shear force at A minus a 2 kilonewton point load minus VB1 is 0. So that gives VB1 is minus 1.75 kilonewtons. So as expected, due to this 2 kilonewton jump, we have a shear force of minus 1.75 kilonewtons. And that's constant on this segment because it has a point load acting on it. Now if we take an equilibrium of moments about the overhang, with counterclockwise being positive by convention, we have minus VB2 multiplied by the moment arm, and the hogging moment here is anti-clockwise. So we have plus 1.5 kilonewton meters, and then plus the uniformly distributed load by 1 meter gives the resultant, and then by 1/2 is the lever arm, and that's equal to 0. And solving for VB2, we obtain 3 kilonewtons. So positive 3 kilonewtons is drawn on the top of this beam. And if you assume there's a shear force on the overhang, you can verify that by vertical equilibrium of forces, that shear force is 0. And the shear force diagram is linear on this portion of the beam because there's a uniformly distributed load. And you can also verify that this reaction here is 4.75 kilonewtons, which is equal to the jump in the shear force across the support. We can adapt the sign convention for the shear force and bending moment that we derive for a beam to a column. So remember, if we cut the beam from right to left, for example, we use this sign convention. And to obtain a sign convention for the column in the frame, we simply rotate this sign convention anti-clockwise. So here, for example, if we cut the column from bottom to top, then we use this sign convention over here. So essentially this column will deform something like this under that point load, because we have a rigid support, so there's no rotation allowed at this joint, so the column behaves like a cantilever. And in frames, the beams are rigidly connected to the columns, so before and after deformation, the beam and column remain at 90 degrees at the joint. So here we can observe the beam is going to be in tension on the top, so the deformed section will look something like this, and the column will be in tension on the left, so the deformed section will look something like this. Let's draw the shear force and bending moment diagram for this frame. And we have a rigid support, so we're going to have a horizontal reaction counteracting that 1 kilonewton load by horizontal equilibrium, and by vertical equilibrium of forces we have a 2 kilonewton reaction counteracting the external load. And because it's a fixed support, we also have a moment reaction to prevent rotation. So if we take a sum of moments about this support, with our usual convention. Then we have the moment m minus 1 kilonewton by the moment arm, and then minus 2 kilonewtons by the moment arm, which both cause a clockwise moment. So therefore the moment reaction is 4 kilonewton meters. And now let's first draw in our shear force diagram. And I'll remind you of the convention that we use when we cut the beam and the column. So I'll draw those in quickly. And we rotate this positive sign convention for the beam anti-clockwise to get our positive sign convention for the column. So if we cut the beam from right to left, we use this convention. And we can see that the shear force is 0 up to the point load. And if we again cut the beam from right to left, we can see that the shear force is constant at 2 kilonewtons by a vertical equilibrium of forces. So that's our shear force diagram, constant at 2 kilonewtons for the beam. Now if we cut the column from bottom to top, we use this sign convention on the top, and we can see that by horizontal equilibrium of forces, the shear force is constant at 1 kilonewton in the column. So this here is our shear force diagram for the frame, where we draw the positive diagram on the top of the beam and to the left of the column. And now let's draw in our bending moment diagram. Well, without taking moment equilibrium to find the bending moment in the column, we know that the bending moment at the fixed support is equal to the moment reaction of 4 kilonewton meters. And we know that the bending moment on the right of the point load is 0, and to the left of the point load is simply going to be the point load by the moment arm. That will be 2 kilonewtons by 1 meter, or 2 kilonewton meters. And because there's no externally applied moment at the joint, the bending moment in the beam is going to be the same as that in the column. And there's no load acting on the column, so that's going to vary linearly to 4 kilonewton meters. So here we normally write the magnitudes, but this indicates that the beam is hogging and the column is in tension on the left. So what the bending moments will look like at the joint: for the beam it looks something like this, and for the column it looks something like this. So these will counteract each other such that the net bending moment at the joint is 0. Let's draw the shear force and bending moment diagram for this frame. Well, by vertical force equilibrium, we have a vertical reaction that's equal to the resultant of the uniformly distributed load, which is 2 kilonewton per meters by the length on which it's acting. And because it's a fixed support, we also have a moment reaction. So taking a sum of moments about the support, with our usual counterclockwise convention being positive, we have a moment produced by the uniformly distributed load that's clockwise, and the resultant has a magnitude of 2 kilonewton per meter by 2 meters, and it acts in the middle of that load. So therefore the moment arm is 1 meter. And then plus the moment reaction is equal to 0. So the moment reaction is 4 kilonewton meters. And we'll first draw the shear force diagram. Well, if we're going to cut the column from bottom to top, we can see that there's no horizontal reaction acting on this segment. So the shear force in the column is all 0. And here we have a uniformly distributed load. So if we got the beam from right to left, so we can see that the shear force is 2 multiplied by x. And therefore it's going to vary linearly on that beam, with a magnitude of 2 by 2 meters, which is 4 kilonewtons. And now we'll draw the bending moment diagram. So here we have a uniformly distributed load. So the bending moment diagram is going to vary from 0 and parabolically up to the joint between the beam and column. And it's simply going to be W by the length, and the resultant acts in the middle of that beam. So we're going to multiply this by the moment arm, which is 2 on 2. And therefore the magnitude of the bending moment is 4 kilonewton meters. And that has the same magnitude as the bending moment in the column, because there's no externally applied moment at the joint. And we can see that there's no horizontal reaction acting on this segment, so the bending moment is going to be constant throughout that column. And at the support is going to be equal to the moment reaction. So remember that the derivative of the bending moment is the shear force. So the bending moment diagram is constant on the column, so the shear force is 0. And the bending moment diagram is parabolic on the beam, so the shear force is linear. Let's draw the shear force and bending moment diagram for this frame. Well, a roller does not have a horizontal reaction, so only the pin is going to resist that horizontal 1 kilonewton load by horizontal equilibrium of forces. And we also have a vertical reaction at the pin and roller. So if we take a sum of moments about the pin, with anti-clockwise being positive, then we have minus 1 kilonewton by the moment arm, minus 2 kilonewtons by the moment arm, and then plus the reaction By by a moment arm of 3 meters is equal to 0. So By is 1.33 kilonewtons. And if you take a vertical sum of forces, with upwards being positive, we have AY plus BY minus 2 kilonewtons is 0. So that gives AY is 0.67 kilonewtons. And now we'll draw the shear force diagram. And what I'm going to do is break up this frame into column and beam members to get a better visual. So if we cut the column from bottom to top, we have the shear force being constant at 1 kilonewton in the column. And if we cut the right column, we can see there's no horizontal reaction, so the shear force is 0 in this column. Now for the left column, we had a reaction of AY, which was 0.67 kilonewtons. So for this column to be in equilibrium, we must have an equal force on the top of the column. And by Newton's third law, we have an equal and opposite force acting on that beam, which has the same magnitude. So this force causes a jump in the shear force diagram of 0.67 kilonewtons. And then up to the 2 kilonewton load, the shear force is constant. And a 2 kilonewton load causes a jump in the shear force downwards. So therefore 0.67 minus 2 is minus 1.33 kilonewtons. And the shear force is constant thereafter. And that final jump is equal to By, because by the same argument we have 1.33 kilonewtons on this column, so therefore we have 1.33 in the top to put in equilibrium, and consequently 1.33 kilonewtons acting on that beam. And now we'll draw in the bending moment diagram in a similar way by breaking up the members. So if you visualize the deformation of this frame, this column here is going to behave like a cantilever with a point load acting at the end of it. So if you cut that cantilever, we can see that the bending moment is the force by the moment arm. So the bending moment at the top of the column is 1 kilonewton by 2 meters, which is 2 kilonewton meters. And because there's no externally applied moment at the joint, this bending moment is equal to that in the beam. Now on the other side, we saw that the beam had 1.33 kilonewtons acting on it, so 1.33 by the moment arm, which is 2 meters up to the point load. So that gives 2.66 kilonewton meters where the point load is. And the bending moment diagram is piecewise linear in that beam because there's only a point load acting on it. And you can also observe that there's no horizontal reaction in the roller, so therefore the bending moment in that column is 0. Let's draw the bending moment diagram for this frame, which is subjected to multiple loads, and we can simplify the problem by superimposing two cases with the loads applied separately to them. And we can plot the bending moment diagram for each case separately to obtain a final bending moment diagram. So for this first case, the pin resists the point load because the roller does not have a horizontal reaction, and therefore the bending moment on this column on the right is all 0. Now on the left here, the bending moment is that reaction by the moment arm. So that will be 1 kilonewton by 2 meters, or 2 kilonewton meters. And the magnitude of bending moment in the beam is equal to that in the column at the joint because there's no externally applied moment. So therefore we have 2 kilonewton meters in the beam also, and that decreases linearly to 0 because as we saw, this column has 0 bending moment. Now for this second case, there's no bending moment in the columns because there's only a vertical load applied to the frame, but we have vertical reactions at the pin and roller. So if we take an equilibrium of moments about the roller, with anti-clockwise being positive by convention, we have minus AY by the moment arm of 3 meters and plus 2 kilonewtons by the moment arm of 2 meters. And that's equal to 0. So therefore AY is 1.33 kilonewtons. And if we take a free body of the left column, we have AY acting on it in the bottom. So therefore, for vertical equilibrium to be satisfied, we must have the same force acting on the top. And by Newton's third law, we have an equal and opposite force acting on the beam. So that's also 1.33 kilonewtons. And therefore the bending moment diagram is obtained as simply this reaction force by the moment arm of 1 meter. So that would be 1.33 kilonewton meters. And remember that the bending moments in the columns were 0 because there's no horizontal reactions. So therefore this decreases linearly to 0. And now we can superimpose these two bending moment diagrams. So at the point load over here, we can use similar triangles to obtain a bending moment at the point load. So that will be 2/3 multiplied by 2 kilonewton meters, which is 1.33 kilonewton meters. So on the beam, we have 2 kilonewton meters plus 0 is 2 kilonewton meters, and then 1.33 kilonewton meters plus 1.33 at the point load, so that would be 2.66 kilonewton meters. And the bending moment diagram is linear. Now at the other end, we have 0 plus 0, so the bending moment at the joint is 0 in the beam. And now for the right hand column, we have 0 plus 0, so the bending moment in the right hand column is 0. And for the left hand column, we have 2 kilonewton meters plus 0 is 2 kilonewton meters. And that's our final bending moment diagram. We can also use the method of superposition to determine a shear force diagram for a frame subjected to multiple loads. So here we superimpose two cases with the loads applied separately. And for the first case, by a horizontal equilibrium of forces, we have 1 kilonewton acting at the pin. And we know there's a vertical reaction at the pin, which I'll assume is acting downwards, and a vertical reaction at the roller, which I'll assume is acting upwards. Because this point load is causing tension in this column and compression in this one. And if we take a sum of moments about A, with anti-clockwise being positive, we have By by the moment arm of 3 meters minus 1 kilonewton by the moment arm of 2 meters is equal to 0. And therefore By is 0.67 kilonewtons. And by vertical equilibrium of forces, Ay is also 0.67 kilonewtons, but acting downwards. And now if we cut the column, we can see that the shear force is constant at 1 kilonewton. Now on the other side, if we take a free body off the right column, we have the reaction By acting on that column. And by vertical equilibrium, we must have an equal and opposite force acting on the top. And therefore by Newton's third law, we have an equal and opposite force acting on a beam of 0.67 kilonewtons. And now if we cut the beam from right to left, and therefore the shear force is negative and constant across that beam at minus 0.67 kilonewtons. And if we cut this column, the shear force in the column is 0, because there's no horizontal reaction at the roller. Now for the second case, you can also find the reactions for the pin and the roller by taking equilibrium of moments, for example, about B, with anti-clockwise being positive, we have minus Ay by the moment arm plus 2 kilonewtons by a moment arm of 2 meters. And that's equal to 0. So Ay is 1.33 kilonewtons. And by vertical equilibrium of forces, with upwards being positive, we have Ay plus By minus 2 kilonewtons is 0. So By is 0.67 kilonewtons. And by the same argument here, by Newton's third law, we'd have an equal and opposite force to that in the column acting on the beam. So that would be 1.33 kilonewtons. And this causes a jump in the shear force diagram of 1.33 kilonewtons. And then you have a jump due to the point load of 2 kilonewtons So the shear force is minus 0.67 kilonewtons in the beam. And we can see that this is also equal in magnitude to the reaction By at this end. Now if you cut both columns, there's no horizontal reactions, so the shear force in the columns is 0. And now we can superimpose both cases. So I have the shear force in the beam of 1.33 kilonewtons minus 0.67 gives 0.66 kilonewtons. And here we have minus 0.67 minus 0.67 gives minus 1.34 kilonewtons. So you can see it's equal to that jump. And now in the left column, we have 1 kilonewton plus 0 gives a shear force of 1 kilonewton in the left column. That's constant. And in the right column, we have 0 plus 0. So the shear force in this column on the right is 0. Let's draw the shear force diagram for this frame from the bending moment diagram. So what we'll do is take a free body of the columns and beam, effectively just cutting them just inside the joints. And therefore we expose a shear force on both sides of the column. And I'll remind you of the sign convention that we use for the column. And from the bending moment diagram, we have tension on the inside of the column, so that's where we draw the tail. And the bending moment in the column is equal to 2 kilonewton meters near that joint. So if we take an equilibrium of moments on the top of the column, with anti-clockwise being positive, we have minus shear force 1 by the moment arm of 2 meters plus 2 kilonewton meters is equal to 0. And therefore V1 is 1 kilonewton. And by horizontal equilibrium of forces, that's also equal to V2. So therefore the shear force diagram in this column is constant with a magnitude of 1 kilonewton. Now in the other column we can do the same thing. So we have our shear force using the bottom sign convention and shear force 2 using the top sign convention. But here we have a zero bending moment diagram. So if we take moments about this point, then we're going to see that V1 is 0. And by horizontal equilibrium of forces, V2 is also 0. So therefore the shear force in this column is 0. Now on the beam, we have an external point load acting. And by cutting the beam just after the joint, we expose an internal shear force and another one on the other side, where we cut it before the joint. And we can see we have a sagging moment in the beam. So we're going to have a bending moment of 2 kilonewton meters. And on the other side, the bending moment is 0 from the bending moment diagram. And now if we take an equilibrium of moments about 0.2, with anti-clockwise being positive, we have minus shear force 1 by the moment arm, which is 3 meters, plus the 2 kilonewton load by the moment arm of 2 meters, and then minus 2 kilonewton meters, and that's all equal to 0. So that gives V1 is 0.7 kilonewtons. So here we draw the shear force diagram on top of the beam because the shear force is positive. And now we can follow the externally applied load. So what we get is minus 1.3 kilonewtons at the bottom. And that's our shear force diagram. Now alternatively, you can take a vertical equilibrium of forces and you'll find that V2 is minus 1.3 kilonewtons. To determine if a frame is stable, we can cut it at some point and expose the internal forces in each part of the frame. So from left to right, we use this convention where the tensile axial force is positive, and on this side we use the left hand positive convention. So here we have two parts with 3 equilibrium equations per part. So that gives us 6 equilibrium equations. And here we have 3 unknown reactions plus 3 unknown internal forces, because these forces and moments here are equal and opposite to these. So therefore we have 6 unknowns. And because the number of unknowns is equal to the number of equations that we have to solve for them, then this frame is stable. And as we did with trusses, if this were a roller, then we'd have less unknowns than the number of equations to solve for them, and therefore the system in this case is overdetermined. And you can see the frame is unstable, because if we were to apply a load to it here, it'll just roll forever. And similar to trusses, if we had this roller oriented as follows, and we had another roller over here, well, the lines of action in this case are going to pass through a common point. So therefore, if we take a sum of moments about this point, then we can see that the externally applied load is going to cause the frame to rotate about this point. And because the reactions pass through that point, they're not going to provide any rotational resistance. And therefore this is another case where the frame is unstable, where we have the same number of unknowns as the number of equilibrium equations to solve for them. Let's draw the shear force and bending moment diagram for this frame with an oblique member. And by vertical equilibrium of forces, we have 2 kilonewtons acting upwards, and a horizontal equilibrium of forces, we have 1 kilonewton acting to the left. And because it's a fixed support, we have a moment reaction. So by equilibrium of moments about the fixed support, with the anti-clockwise being positive, we have minus 1 kilonewton by the moment arm, minus 2 kilonewtons by the moment arm, which is 4 cosine 30 degrees. And plus the moment reaction is 0. And if we draw in our special trig triangle for the angle of 30 degrees, we have root 3, 1 and 2. So therefore cosine 30 is the adjacent on the hypotenuse. And our moment reaction is 3 plus 4 root 3 kilonewton meters. And now let's draw our shear force diagram over here. Well, what we do is resolve this 2 kilonewton force into a component that's perpendicular to the beam. And this angle here is 30 degrees, and so is this one. So this component of the force is 2 cosine 30 degrees, or 2 root 3 on 2, or root 3. And now if we cut the beam as follows, the shear force is root 3 and constant along that beam. And at the bottom we have a horizontal reaction. So if we cut the column as follows, the shear force is 1 kilonewton and constant in that column. And now we'll draw in our bending moment diagram. So the bending moment in the beam is √3 by the moment arm, or 4√3, and varies linearly along that beam. And at the joint there's no externally applied moment, so the bending moment in the beam is the same as that in the column. And the bending moment at the support is equal to the moment reaction. So that will be 3 plus 4√3 kilonewton meters. And the bending moment here varies linearly along the column. Consider this body in the xy plane, and here we have another view of the body with the z-axis pointing upwards, and the body is broken up into a set of particles. And the force of weight due to gravity acting on each particle is shown. And therefore, the resultant or total force of weight is equal to the sum of the forces of those weights on each particle, from I equals 1 to the number of particles. Now if we take a sum of moments about the y-axis, then the moment produced by the force of weight acting on each particle is the moment arm multiplied by the force of weight. And the total moment produced is obtained by summing up all these moments. And here we set this equal to the moment arm multiplied by the resultant force. So we expect the resultant's going to act on his body where most of the weight is, and produce some moment about y, with the moment arm being x bar. Now if we substitute for the resultant force using this expression, we obtain the following expression where we have x bar by the resultant force defined by this sum is equal to the total moment produced, which is defined by the sum of moments on the right hand side. And now if we divide through by this term, we obtain an expression for the centroid for a discrete body. And now if we take the limit as the number of particles approach infinity, we obtain a definition of the centroid for a continuous body. So we're integrating x with respect to dfw, which is a force of weight acting on an element of the body, over the integral over dfw. Now the force of weight can be written as the density by gravity by the volume of a body. So therefore the body with a uniform density and a uniform gravitational field acting on it, then the force acting on a differential element is ρg by the volume of that element. And because we're trying to find the centroid of an area, we can take this body as having a uniform thickness or a unit thickness. So therefore the differential volume element having a uniform thickness can be written as the thickness out of the plane by dA, being the differential area. And if you substitute this for dV, we obtain ρg by the thickness by dA. And now we can substitute into this expression, and we obtain an expression for the centroid as an integral over an area. So that'll be x by ρgt dA over the integral of rho gt dA. And as we said, for a body with a uniform density and a uniform thickness and a uniform gravitational field, we can take these out of the integral and cancel them. And therefore, our expression for the centroid is the integral over the area, and we're integrating x over dA, and that's divided by the integral over the area of the body. And to obtain an expression for the centroid in the y direction, well, you take moments about the x-axis, and you'll obtain an integral of y over the area over the integral over the area of the body. To find the centroid of a composite section, we can break up the expression for the centroid using piecewise integrals. So we can integrate over the area of section 1, so we integrate x over the area, and we do the same thing by integrating over the area of section 2. And basically this distance x is measured from some origin. And we divide this by the integral over area 1 plus the integral over area 2. Effectively evaluating the integral in the denominator piecewise. Now, using the definition of the centroid, we can write the integral of x over the area as the centroid of that area by the integral over that area. So effectively we can rewrite these integrals in a numerator as the centroid of area 1 by the integral over area 1. And we can do the same for area 2. So effectively we integrate over area 2, and in the denominator we have the integral over area 1 plus the integral over area 2. Now, for prismatic sections, where we can calculate the areas using geometry, we can evaluate the centroid of the entire composite section, where the centroid of area 1 is measured from some origin, and we multiply this by the area of the simple shape. And we do the same thing for area 2. So here we have the centroid of area 2 measured from the same origin, and this is divided by area 1 plus area 2. And in general, this centroid can be written as follows. So we sum over the centroids of all the areas, multiplied by those areas, divided by the sum of those areas. And similarly, you can have an expression for the centroid of the composite section in the y direction by replacing the centroids of those areas with that in the y direction. Let's find the centroid of this triangle. And what we'll do is find x bar first. So we break up this triangle into infinitesimally thin areas, and this differential area is equal to y by dx. And considering this triangle has a height h and width b, the slope of this line is therefore minus h on b. And then multiplying by x and adding the y-intercept gives the equation of that line. So therefore we can rewrite this integral as an integral from 0 to b, and we have x multiplied by dA. So that will be y, which is this term, which is minus h on b by x, plus h, and we integrate over x. And that's divided by the integral from 0 to b of dA, which is minus h on b by x plus h, and we integrate with respect to x. Now we know this integral here is going to evaluate to bh on 2, which you can verify as the area of this triangle. And now if we evaluate the integral in the numerator, we have minus h on b by x squared, so it'll be x cubed on 3, and then plus h by x squared on 2. And we evaluate this from 0 to b. And that's divided by bh on 2. So therefore we have minus h by b cubed on 3b plus hb squared on 2. And that's divided by bh on 2. So one of these b's will cancel, and another b will cancel with this one, and h will cancel with this one. So what we get is minus b on 3 plus b on 2 over a half. So 1/3 is the same as 2/6, and 1/2 is 3/6. So what you get is 1 on 6 on a half, or b on 3. And this is a well-known centroid of a triangle, which is 1/3 of the distance from this side. And I'll leave it for you to evaluate this integral to verify that y bar is equal to h on 3. Let's find the centroid of this T-section, and to do that we'll take our origin at the bottom corner. So what we'll have is x going this way and y going this way. Now by symmetry, you'll notice that the x component of the centroid is in the middle of this T-section, which is 150 from the origin, and we'll assume units of millimeters here. And I'll leave it for you to verify this using this equation. And now let's use this equation to calculate the y component of the centroid. So what we have is the centroid of the web, and the web has a height of 320 minus 20. So the centroid is directly in the middle of this rectangular section, and then we multiply this by the area of the web. So that'll be 25 millimeters by 300. And plus the centroid of the flange. So from the origin, the centroid is 310 millimeters. So in the middle of this rectangular section. And we multiply this by the area of the flange. And that's divided by the area of the web plus the area of the flange. And if we calculate this out, we obtain 221.1 millimeters. So as we can see, y bar is closer to the top of the flange, because that's where most of the mass of the section is concentrated. We can use the centroid of an area to determine the force resultant of a distributed load. So if we consider this triangular load, this line can have an equation of W by x on L. So at x equals 0, the load is 0, and at x equals L, the load is W. Now if we cut out an infinitely thin rectangle, which has a width dx, and it's at a distance x from some origin, well, this differential force is equal to the height of this rectangle, which is Wx on L, multiplied by the thickness of the rectangle. And then integrating from x equals 0 to x equals L gives us the force resultant. So if we evaluate this integral, we get Wx squared on 2L, evaluated from 0 to L, and therefore the magnitude of the resultant force is equal to WL squared on 2L, or WL on 2. Now to determine x bar, where the force resultant acts, we evaluate this integral here. So we have x bar by our force resultant, which is WL on 2, is equal to the integral from 0 to L, and we have x being the moment arm, multiplied by the differential force, which is Wx on L dx. And now if you evaluate this integral, you'd have W on L, and we have x squared, that will be x cubed on 3. And we evaluate this from 0 to L. So that gives WL cubed on 3L, or WL squared on 3. And that's equal to x bar by WL on 2. And now if you solve for x bar by dividing through by W and dividing through by L, and then multiplying through by 2, we obtain x bar is 2/3 L. And that's expected that the resultant force acts at 2/3 of the length of this distributed load. And I'll leave it for you to do the same for this parabolic distribution. So that may have an equation of W by x squared on L squared. And you can find the force resultant and the centroid at which it acts. The second moment of area has a similar expression to the centroid of a section, but it involves a square of the moment arm. And it comes up as a geometric quantity of a section in resisting a bending stress. So for example, if a stress is applied to this area, and it's a vector coming out of the plane, then it can cause bending rotations about the x-axis and also about the y-axis. So the resisting quantity for bending rotations about the x-axis is the second moment of area about this axis, which involves the square of the moment arm multiplied by the differential area, and it's integrated over the area of the section. And similarly, the second moment of area about the y-axis has a squared moment arm of x squared. Now if a stress was applied in the xy plane, such as a shear stress, well, this can cause rotations about the z-axis. So if we consider this distance as r, then by Pythagoras' theorem, we have r squared is x squared plus y squared. And if we integrate this over the area of the section, then we obtain the following expression on the right hand side, which is x squared plus y squared integrated over the area. And if we break up the integral on the right, we obtain a moment of inertia about the y-axis plus the moment of inertia about the x-axis. And this quantity here is the polar moment of area, which we denote IZZ which is equal to ixx plus iyy. Now if we consider this example, and we want to find the second moment of area about the horizontal axis, well, we'll break this section up into infinitely thin rectangles, and these have a thickness dy, and the section has a width b and a height h. So therefore the differential area is b dy, and we multiply this by y squared and integrate this from minus the height on 2 to plus the height on 2. And if we take b outside the integral, then we obtain y cubed on 3 evaluated from minus h on 2 to h on 2. So that gives b by h cubed on 3 by 8, which is 24, minus negative h cubed on 24. Which gives bh cubed on 12. And that's a well-known second moment of area for a rectangular section about the horizontal axis. And I'll leave it for you to verify that the second moment of area about the y-axis is equal to hb cubed on 12. And you can verify this by taking your infinitesimally thin rectangle in the vertical direction and integrating over x. We can use the parallel axis theorem to determine a second moment of area about an arbitrary axis, using the known second moment of area about the centroidal axis. Now recall that the second moment of area about an axis x was the integral of the squared distance to the differential area over the area of the section. Now we can split up the y distance as the distance from that area to the centroidal axis plus the distance from the centroidal axis to the axis where we're taking the moment of inertia about. And that's integrated over the area. And now we can expand the integrand. So we have yc squared plus 2yc dcy plus dcy squared integrated over a. And now we can split this up into multiple integrals. So we have the integral of yc squared over the area plus 2 by dcy by the integral of yc over the area. And note that dcy is constant, so we took it outside the integral. And then we have plus dcy squared taken out of the integral by the integral over the area of the section. Now this integral here is going to evaluate to 0 because you're going to have elements on both sides of the centroid where their first moments of area cancel. And therefore we're left with this integral, which is the second moment of area about the centroid, and then plus the area of the section multiplied by the squared distance between the centroidal axis and the axis that we're taking a moment of inertia about. And this here is known as the parallel axis theorem, where we can use a second moment of area about the centroid to find a second moment of area about any other axis. And we have a similar expression for the second moment of area about the y-axis using the second moment of area about the y-axis of the centroid, plus the area by the distance between the centroidal y-axis and the y-axis where we're taking the moment of inertia, and that's squared. And recall that the polar second moment of area was equal to the second moment of area about the x-axis plus the second moment of area about the y-axis. So if you substitute these expressions, we obtain Ixx bar plus Iyy bar plus the area by dcx squared plus dcy squared. And now for this example rectangular section, we know the second moment of area about the centroidal axis, which is the width of the section by the height of the section cubed on 12. And suppose we want to find the second moment of area about this x-axis. Well, the distance between the centroid and this axis is the height of the section on 2, and the area of the section is the width by the height. So using the parallel axis theorem, dcy squared is h on 2 squared. And that's equal to the second moment of area about the x-axis. So doing some algebra, we have bh cubed on 12 plus bh cubed on 4, which is 3 bh cubed on 12. And that's equal to 4 bh cubed on 12, or bh cubed on 3. Let's find a second moment of area of this triangle about the centroid. To simplify this problem, we can use a parallel axis theorem to find a second moment of area about the x-axis, and then solve this equation to find a second moment of area about the centroid. And we know that the centroid is located at 1/3 of the height of the triangle. Now the second moment of area was the integral of y squared over the area of the triangle. And the differential area here is equal to x dy. And given this triangle has a height h and width b, then we can write the equation of this line as the slope, which is minus the rise over the run, by x plus the y-intercept. And we can solve this equation for x by subtracting h from both sides, and then multiplying through by negative b and dividing through by h. And that's equal to x. And therefore we can rewrite the second moment of area as an integral from 0 to the height of the triangle, and we have y squared dA, which is x, or minus b on h, by y minus h dy. And now we can simplify this integral by taking the constant outside. So we have the integral from 0 to h y cubed minus y squared h, and we integrate this over y. And now we can evaluate this integral. So we have minus b on h multiplied by y to the 4 on 4 minus y cubed h on 3. Evaluated from 0 to h. So we end up with minus b on h by h to the 4 on 4 minus h to the 4 on 3. So that would be 3 on 12. And 1/3 is 4 on 12. So we get minus b on h multiplied by minus 1 on 12 by h to the 4. So therefore, Ixx is bh cubed on 12. And now we can use the parallel axis theorem to solve for the second moment of area about the centroid. So we have bh cubed on 12 is equal to Ixx bar plus the area of the triangle, which is half the base by the height, multiplied by the squared distance between the centroid and the x-axis. So that will be h on 3 squared. And therefore we have Ixx bar is equal to bh cubed on 12 minus bh cubed on 2 multiplied by 9. And 1 on 12 is 3 on 36. And 1 on 18 is 2 on 36. And therefore Ixx bar is bh cubed on 36. Let's find a second moment of area about the centroid of this T section. Well, what we can do is break this up into two areas, being the area of the flange and the area of the web. And therefore we can use the following equation to determine the second moment of area of each of those areas about the centroid of the section. So for each rectangular section we have the width by the depth cubed on 12 plus the area of the section multiplied by the distance between the centroid of that area to the centroid of the section squared, using the parallel axis theorem. So therefore the second moment of area of the entire section about the centroid is equal to the contribution from the flange, so that will be the width by the depth cubed on 12 plus the area of the flange, which is 300 by 20, and then we multiply this by the distance of the centroid of the flange to the centroid of the section. So using geometry, you can work out that the distance at the top of the section is 98.9 millimeters. So therefore dcy is equal to 98.9 minus this distance over here, which is 10 millimeters. And that's squared. And now we add the contribution of the web. So that'll be 25 by the perpendicular dimension cubed. So that'll be 320 minus 20, which is 300 on 12. And then plus the area of the web. That's multiplied by the distance of the centroid of the web to the centroid of the section. So that would be 221.1 minus this distance over here, which is 300 on 2. And that's squared. So if you calculate this out, you'll get 1.4 by 10 to the 8. And assuming units of millimeters for this section, the unit will be millimeters to the 4. Now to calculate the second moment of area about the y-axis of the centroid, well, that's simply equal to the depth by the width cubed of each section on 12. So what we have is I bar is equal to the width, which is the parallel dimension, multiplied by the perpendicular dimension to the y-axis cubed. That'll be 300 cubed on 12. And that's the contribution of the flange. Then plus the contribution of the web, which is 300 by the perpendicular dimension cubed on 12. So that gives 4.5 by 10 to the 7 millimeters to the 4. And here there's no parallel axes terms because the centroid of the flange and the web coincide with the centroid of the section, and as we can see, the second moment of area about the y-axis of the centroid is much smaller than that of the second moment of area about the horizontal axis, because there's a larger distribution of area in the vertical direction. Let's find the second moment of area of this circle about the horizontal axis. So the definition is the integral over the area of the section, and we're integrating y squared. And here we can see that dA, being the differential area, is equal to x by dy. And to obtain an expression for x, we're going to use polar coordinates. So we have this distance is the radius r, which is at some angle theta from the horizontal axis. So using Pythagoras' theorem, where this distance is y, we have x squared plus y squared is r squared. And therefore x is r squared minus y squared to the 1/2. Then we can substitute for dA in this integral. So I have the integral of y squared by r squared minus y squared to the 1/2. So that's x, and we're integrating over y. And here we're going to integrate from y equals 0 to y equals r, and that's going to give us a contribution of the second moment of area of 1/4 of the circle. So to obtain a net second moment of area, we'll just multiply this by 4. And now we can introduce a change of variables. So using polar coordinates, we have y is r sine theta, and therefore dy is equal to r cosine theta d theta. And therefore we can rewrite this integral as an integral over theta. So we integrate from theta equals 0 to theta equals pi on 2, or 90 degrees. And y squared is r squared sine squared theta, and that's multiplied by r squared minus y squared, which is r squared sine squared theta to the 1/2, and dy is r cosine theta d theta. And now we can do some algebra. So we can rewrite the integral as r cubed sine squared theta by cosine theta. And here we can factor out r squared, and we have 1 minus sine squared theta to the 1/2 integrated over theta. So using the trig identity, this is cosine squared theta. So we can simplify the integral as the integral from 0 to pi on 2. And here we have r squared to the 1/2. So that'll be r multiplied by r cubed is r to the 4. And then we have sine squared theta. And then cosine squared to the 1/2 is cosine theta multiplied by cosine theta gives cosine squared theta. And now we can use the double angle trig identities, which I'll write here for your reference. So we end up with the following expression, where we take r to the 4 outside the integral. And what I'll do is take out these halves also, because we're going to multiply them out. So we end up with 1 minus cosine 2 theta by 1 plus cosine 2 theta. So that would give 1 minus cosine squared 2 theta integrated over theta. And the 4's cancel, so we have r to the 4 by the integral from 0 to pi on 2. Then we have 1 minus cosine squared 2 theta, which, using the double angle trig identity, by replacing theta with 2 theta, so this becomes 4 theta, and we have 1 half by 1 plus cosine 4 theta, and this is all integrated over theta. And we can simplify this a bit further, so we have r to the 4 by the integral from 0 to pi on 2, and 1 minus a half is 1 half, and then we have minus 1 half cosine 4 theta integrated over theta. So that gives r to the 4 on 2, and evaluating the integral gives theta minus a quarter sine 4 theta, evaluated from 0 to pi on 2. And therefore sine of 4 pi on 2 is 0, and sine of 0 is 0, so this term is 0, and we end up with the second moment of area is equal to r to the 4 on 2 multiplied by pi on 2, which gives pi r to the 4 on 4. Let's find the second moment of area of this section about the horizontal axes. So what we'll do first is evaluate the polar moment of inertia, which is the integral of r squared over the area, and then using the following relationship between the polar moment of inertia and ixx and iyy, we can obtain ixx. So here we'll take an infinitely thin circular ring which has a width dr, and the distance from the origin to this ring is r. So therefore the differential area of that ring is 2 pi r, being the circumference, and multiplied by the thickness. So effectively we're rolling it out as a rectangle. And now we can substitute this in the expression for the polar moment of inertia, where we're integrating from r equals 0 to the radius of the circle r. So we have r squared by dA, which is 2 pi r dr. So we can take 2 pi outside the integral, and then integrating r cubed gives r to the 4 on 4, and that's evaluated from 0 to r. So therefore we have 2 pi multiplied by r to the 4 on 4. So therefore the polar moment of inertia is equal to pi r to the 4 on 2. And recognizing that the circle is symmetric, ixx is equal to iyy. So we have izz is 2ixx, and the polar moment of inertia is pi r to the 4 on 2. And solving this equation gives a second moment of area about the x-axis as pi r to the 4 on 4, which is the same result we got in a previous video using the more difficult method. Consider a beam subjected to a transverse load And if we cut the beam somewhere along the length, we have a sagging moment causing tensile stresses in the bottom and compressive stresses in the top. And at the centroid, which may not be in the middle of the beam, depending on the section, the stress is 0. Now on a small area element of this section, which may have some arbitrary shape, and the section is in the xy plane, and we'll look at some differential area element that the differential force is acting on. So the differential moment is the moment arm from the centroid of the section, which is y by df. And this can be written as follows by recognizing that the differential force is the stress acting on this differential area element. And now we can integrate both sides to get an expression for the bending moment as equal to the integral of y by the stress over the differential area. Now we can recognize that this bending stress distribution is linear, so we can relate the stress on the top of the section on the distance from the centroid, yc, to the stress acting on a differential element. So that would be some stress over the y distance from the centroid. And if we multiply through by y, we can rewrite this stress as stress C on yc, which we can take outside the integral because it's constant, and that's multiplied by the integral of y squared dA. And this ratio is simply equal to stress on y acting anywhere along that section, and this integral is the second moment of area. So therefore we can write the bending stress as m multiplied by y on the second moment of area. And because we want tensile bending stresses to be positive, at a negative y value along that section, and where the sagging moment is positive, then positive by negative will give a negative stress. So to make the tensile stress positive, we'll put a negative over here. So where y is positive, we have the sagging moment causing compression, and because m and y will be positive in this case, we have the compressive stress being negative. And this will also be true where we have a hugging moment causing tensile stresses in the top of the beam. So because the hugging moment will be negative and y will be positive on the top of the beam, and negative of negative gives a positive tensile stress on the top of the beam. So have a think about this. Consider the deformation of this beam under external loads. And if we take a small element of the deformed shape, which has an arc length ds, that's equal to rho being the radius of curvature by the differential change in the angle. Now if we blow this up into a right triangle, we have ds and a differential length dx and a differential change in the vertical deflection dv. So using Pythagoras' theorem, we can write this as ds squared is dx squared plus dv squared. And the third relationship is tan of the angle theta is equal to dv dx. Now if we differentiate this expression with respect to x, applying the chain rule, we get sec squared theta by d theta dx is equal to the second derivative of v with respect to x. And applying the following trig identity of cosine squared theta plus sine squared theta is 1, If we divide through by cosine squared theta, we get 1 plus tan squared theta is sec squared theta. And tan squared theta is simply dv dx squared. So therefore we can write sec squared theta using this expression as 1 plus tan squared theta, or dv dx squared, and that's multiplied by d theta dx is equal to the second derivative of v with respect to x. And now if we divide through by this term, we get an expression for d theta dx, which is the second derivative of v with respect to x over 1 plus dv dx squared. Now doing a bit of algebra on this equation, we have ds squared is dx squared, which will factor out, and that gives 1 plus dv dx squared and then you can divide through by dx squared and take the square root of both sides, and therefore we obtain ds dx is equal to 1 plus dv dx squared to the 1/2. And for this equation, we can divide through by dx, and we get ds dx is rho d theta dx. And now we can substitute these expressions in this equation, which I'll quickly write down. And if we divide through by the radius of curvature and divide through by this equation, we get this expression in the denominator to the 1 plus 1/2, or to the 3/2. So therefore our final equation for the curvature is written as follows. Now in structures, we look at very small deformations of the beam, so the rotations are much less than 1. So therefore the square of a small term, where theta is dv dx, is much smaller than 1. So we end up with the following curvature expression for small deformations in Cartesian coordinates. The Euler-Bernoulli beam is central to structural engineering and typically involves a beam with a span to depth ratio that's quite large. So the theory applies to very thin beams. So for example, with a span to depth ratio greater than 20, so we can neglect shear deformations that are considered in a Timoshenko beam, which we'll look at later. And the theory assumes that plane sections remain plane. So before and after deformation, the sections remain straight, and they also remain perpendicular to the neutral axes. And the deformation is only considered to be caused by the bending moment. So in this case we have a sagging moment, which is positive. And if we consider this cross section that has a width dx, then before deformation, if we look at a fibre above the neutral axis, then this here has a length ds. And after deformation, the neutral axis remains undeformed, so it has the same length, and the fibre that we looked at, that's at a distance y above the neutral axis, gets compressed in the top and has a deformed length ds dash. And the distance from the center of curvature for the section to the neutral axis is given by the radius of curvature, and therefore the strain in this fibre is equal to the deformed length of the fibre minus the original length of the fibre over the original length of the fibre. So ds dash is the radius of curvature minus y, which gives that distance over here, multiplied by d theta, and then minus the original length of the fibre, which is equal to dx. So that will be rho d theta, and then over the undeformed length of the fibre. So rho d theta cancels with this one, and then the d thetas cancel, so we end up with the strain being minus y on the radius of curvature, where y is the distance of the fibre from the neutral axis. Now recalling our equation for the bending stress, which is minus the bending moment by y on the second moment of area, and we had a negative sign to make tensile stresses positive and compressive stresses negative. And for a linear elastic material, the Young's modulus is the stress on the strain. So therefore, the strain is the stress on the Young's modulus, which means that the strain is equal to minus my on EI. And now we can cancel out the y and a negative sign, so that gives the curvature is equal to the bending moment on the bending stiffness EI. And if we multiply through by EI, and we derived the curvature in the previous video in Cartesian coordinates as a second derivative of the vertical displacement with respect to x, so we end up with the bending stiffness by the curvature is equal to the bending moment, which is a function of x along the beam. And this here is a moment curvature equation, which is really one of the most important equations in structural engineering. As we saw for the Euler-Bernoulli beam, which are beams that are quite thin, so their span to depth ratio is quite large. For example, the span to depth ratio is greater than 20. And here we assume that shear deformations are negligible and only the bending moments cause deformations of the section. So the bending moment causes this section to rotate and the section stays straight. So plane sections remain plane and the section also remains perpendicular to the neutral axis before and after deformation. So with the Euler-Bernoulli beam, we have a rotation theta and the net rotation of the centroid is equal to theta. And this can be seen if you blow this up into a right triangle. Now with the Timoshenko beam, you have a rotation caused by the bending moment that causes the section to rotate, and here we can see that the section is perpendicular to the old neutral axis without shear deformation. So we have this angle looking something like this, being theta, and this bending deformation causes rotation of the section and the neutral axis. Now if we consider shear deformation, which need to be considered for a Timoshenko beam, which is a lot thicker than the Euler-Bernoulli beam, then you have this additional shear strain, which is a rotation due to the shear deformation. So this shear deformation causes a further rotation of the neutral axis, but it doesn't cause any further rotation of the cross section. So the net rotation of the neutral axis is the bending rotation and the shear rotation. So because the cross section doesn't rotate, as we can see, under a shear deformation, then if we look at some fibre in a beam that's at a wide distance from the neutral axis, so it could be somewhere here, so the displacement of this fibre is purely due to the bending deformation, and because the displacement's to the left, we have minus y by theta, where this angle theta is equal to this angle due to the bending deformation. And we're only looking at deformations in the plane, so we have a vertical deflection that's a function of x for both cases. And now we can calculate the bending strain, which is equal to the first derivative of u with respect to x. So that would be minus y d theta dx. And the tensor strain, epsilon xy, is 1/2 by du dy plus dv dx. So for the Euler-Bernoulli beam, epsilon xy is 1/2 by du dy, which is minus theta, plus dv dx, which is theta. And that's equal to 0. So there's no shear strains in the Euler-Bernoulli beam. And for the Timoshenko beam, epsilon xy is 1/2 by du dy, which is minus theta, plus dv dx. So that will be theta plus gamma. So for the Timoshenko beam, the tensor strain is 1/2 of the shear strain. We derive the following strains for the Euler-Bernoulli beam and the Timoshenko beam, where only the bending strain in the Euler-Bernoulli beam causes a rotation of the neutral axes and the cross section remains perpendicular to the neutral axes before and after deformation. Whereas for the Timoshenko beam, we had bending, which rotates the neutral axes and the cross section, and shear, which further rotates the neutral axes without rotating the cross section. So for the Timoshenko beam, plane sections remain plane, but not perpendicular to the neutral axes after deformation. Now for a fibre on that cross section that's at a distance y from the neutral axes, where we take y being positive upwards, the sagging moment causes a tensile stress in the bottom of the beam and compression in the top of the beam. And we derive the bending stress as equal to the negative of the bending moment by y on the second moment of area. So for a sagging moment which is positive, and a fibre below the neutral axis where y is negative, we have a positive bending stress, which signifies tension. And the bending stress is equal to the Young's modulus by the bending strain. So if we substitute for the bending strain, we obtain the following expression. And we can cancel out the y's and the negatives and write the bending moment in terms of the curvature due to bending. And that's our first equation, which is applicable to both beams. Now for the Timoshenko beam, we need to use an additional relation, being the constitutive relation between the shear stress and shear strain, which is related by the shear modulus. And if we first assume that the shear stress is uniform on the cross section, then we can write this as the shear force on the cross-sectional area, and then substituting for the shear strain, we have the following expression. Now, because we know that the shear stress distribution is parabolic, so for example, for this rectangular cross section, it looks something like this, and the shear stress is a maximum at the centroid. So what we do is multiply the cross-sectional area by a correction factor. And now if we solve for the shear force, we obtain the following expression. But recall that our sign convention was positive. We had a shear couple acting as follows, and sagging moments on the cross section. So this shear couple would distort the section as follows, which basically causes a clockwise shear deformation. And we had counterclockwise angles as positive, so therefore a positive shear couple would cause a negative shear deformation, whereas a negative shear couple would cause a positive shear deformation. So therefore we can rewrite this expression as follows. And we can integrate these expressions to obtain the deflections and rotations of the Timoshenko beam. And recall the derivative of the bending moment is equal to the shear force, and the derivative of the shear force is equal to the negative of the uniformly distributed load. So therefore you can obtain further equations that describe the behavior of the beam. So for example, by differentiating this equation and then equating these two. Let's find a maximum deflection and rotation with the Timoshenko cantilever and compare the result with Euler-Bernoulli. So the governing equations are the bending stiffness by the curvature is equal to the bending moment, and the shear correction factor by the area by the shear modulus multiplied by the negative of the shear angle, which is a bending angle, minus the net rotation of the neutral axis, and that's equal to the shear force. And now we can take a cut of the beam, thereby exposing the internal shear force and bending moment. And this cut segment is at a distance x from the support. So it has a length of L minus x. And therefore using statics, by taking a vertical sum of forces, we see that the shear force is equal to the point load. And then taking moments about this point, we see that the bending moment, which is negative clockwise, minus P by L minus X, being the lever arm, is 0. So therefore the bending moment is equal to P by X minus L. And now we can make those substitutions for the bending moment and shear force. And then integrating the left equation, we have an expression for the bending rotation as px squared on 2ei minus plx on ei plus a constant of integration. And now if we apply the boundary condition where the bending rotation at x equals 0 is 0, then we can see that c1 would be 0. And now we can rearrange this equation for dv dx by dividing through by this term. So we obtain dv dx is equal to theta minus p on kappa ag. And then substituting for theta, we obtain dv dx is px squared on 2ei minus plx on ei minus p on kappa ag. And integrating this equation, we obtain an expression for the deflection. So that will be px cubed on 6ei minus plx squared on 2ei minus px on kappa ag plus a constant of integration. And now if we apply the boundary condition that the deflection at x equals 0 is 0 at the support, well, that would give C2 is 0. And now to obtain a maximum rotation, we just substitute x equals L. So that would give theta at x equals L is equal to PL squared on 2ei minus PL squared on ei, which gives minus PL squared on 2ei, meaning that the bending rotation at the tip of the cantilever is clockwise. And the maximum deflection is a deflection at x equals L. So substituting L, we have PL cubed on 6ei minus PL cubed on 2ei and then minus PL on kappa ag. So this term can be written as 3 on 6. Therefore we obtain minus 2 PL cubed on 6ei minus PL on kappa ag. And 2 on 6 is the same as 1/3. And this here is a maximum deflection, which is negative downwards. And you can substitute for the rotation at x equals L into this expression to obtain a net rotation of the neutral axis, which includes the shear term. Find the maximum deflection and rotation for the simply supported Timoshenko beam and the uniformly distributed load, and compare the result with Euler-Bernoulli. Well, the governing equations are the bending stiffness by the curvature is equal to the bending moment, and the shear correction factor by the cross-sectional area by the shear modulus by the negative of the shear angle, which is the bending angle minus the net angle change of the neutral axis, and that's equal to the shear force. Now if we cut this beam at some distance x from the support, so we expose the shear force and bending moment, well, by symmetry the reaction is WL on 2, and if we're taking a vertical sum of forces, we have minus the shear force acting down plus WL on 2 minus WX is 0. And taking a sum of moments about this point, we have positive M being anti-clockwise minus WL on 2 by the lever arm, which is clockwise, then plus WX by the lever arm X on 2. And that's all equal to 0. And now we can substitute for the moment and shear force, so that will be WL on 2x minus WX squared on 2 and WL on 2 minus WX. Now dividing through by EI and integrating this equation, we get WL x squared on 4EI minus WX cubed on 6EI plus a constant of integration. And by symmetry, we know that the bending angle at halfway in the beam is 0, so that gives 0 is WL by L on 2 squared, so that would be WL cubed on 4 by 4, which is 16 EI, and then minus WL on 2 cubed, so 2 cubed is 8 by 6 is 48, and then plus the constant of integration. And 1 on 16 is the same as 3 on 48. And 3 minus 1 is 2, so we get 2 on 48, which is 1 on 24. So therefore C1 is minus WL cubed on 24 EI. And now solving this equation for dV dx, so first we divide through by kappa Ag. So we get WL on 2 kappa Ag minus Wx on kappa Ag. And therefore dV dx, if we put it on this side, it's equal to theta, which is WLx squared on 4EI, minus Wx cubed on 6EI, and then minus WL cubed on 24EI. And that's minus WL on 2 kappa Ag, and then plus Wx on kappa Ag. And now we can integrate this equation to get an expression for the deflection. Start with WL by x cubed on 12 EI minus Wx to the 4 on 24 EI, then minus WL cubed by x on 24 EI, then minus WLx on 2 kappa Ag, and then plus Wx squared on 2 kappa Ag, plus a constant of integration. Now if we apply the boundary condition that the deflection at the support is 0, the constant of integration is 0. And we know the maximum deflection occurs at midspan, so we substitute L on 2 in this equation. So that would be WL by L cubed over 12 by 2 cubed, which is 96 EI, and then minus WL to the 4 on 24 by 16, which is 384 EI. Then minus WL to the power of 4 on 48 EI minus WL squared on 4 kappa Ag, and then plus WL squared on 2 by 4, which is 8 kappa Ag. So therefore, if we make some simplifications, this is 4 on 384, and this here is 8 on 384. And 1 on 4 is 2 on 8. So what we get is 4 minus 1 is 3, minus 8 is minus 5 on WL to the 4 on 384 EI. And then minus 2 plus 1 is minus WL squared on 8 kappa Ag. And this here is the maximum deflection of the Timoshenko beam. With this component here is the deflection given by the Euler-Bernoulli beam, which doesn't account for shear deformation. Now the maximum rotation occurs at the support, or x equals 0. So therefore, substituting x equals 0, we obtain minus WL cubed on 24 EI. And as we can see, because we got a negative result, that's a negative bending rotation. And if you want the net rotation of the centroid at the support, including shear effects, you substitute x equals 0 in this expression, and what you get is dV dx at x equals 0 is minus WL cubed on 24 EI minus WL on 2 kappa AG. So this is the bending rotation of the Euler-Bernoulli beam, and then minus a shear term, which gives the net rotation of the neutral axes of the Timoshenko beam. And these are our results. Recall that the moment curvature relation for an Euler-Bernoulli beam can be written in this form. So the curvature is equal to the bending moment on the bending stiffness, and the curvature was also the first derivative of the rotation with respect to x. And if you separate the variables, we obtain the following expression. So d theta is m on EI dx, and then integrating both sides, we have an integral from theta a to theta b, and on the right we integrate from xa to xb. And we call this the rotation at b relative to a. So that tells us that the area under the curvature diagram from a to b gives us a change in the bending rotation. Now at some distance x from point A, we can draw a tangent to the curve. So that will be perpendicular to this line. And we can also do the same at x plus dx. So this distance is dx. So we have another tangent drawn from here. That's perpendicular to this line. And therefore this angle here is equal to this angle of d theta. And this line has some length x dash. So the arc length here, dt, is equal to x dash d theta. Similar to this arc length ds being equal to the radius of curvature by d theta. Now for a small angle approximation, the deflection is much smaller and the rotations of the beam are much less than 1. So for that special case, x dash approaches the length x. So therefore we end up with the following expression. And we already saw that d theta is m on EI dx, and that's equal to dt. And if we integrate both sides of this equation, we have the integral from the tangent at A to the tangent at B, and on the right hand side we integrate from xa to xb. So the expression on the left is the tangent at A relative to B, which gives us this length over here. And that can be used to calculate the deflection between the 2 points. Now we can simplify this integral using the definition of the centroid, which was the integral of x over an area over the integral over the area of a section. But here we're integrating over the area of a curvature diagram. So you can replace dA with m on EI dx, and also in a denominator. And if you multiply through by the expression in a denominator, we can write this expression, which is this one over here, as the centroid of the area of the curvature diagram by the integral from xa to xb, and we're integrating the curvature over x. So if you evaluate the relative rotation, you'll be able to just multiply by the centroid of the area, which is convenient if the curvature diagram is linear. and that gives you the distance between the tangents. So these two equations are the ones we'll use to obtain the deflections and rotations using the moment area method. Let's find the maximum deflection and rotation for this beam. Well, if we choose our coordinate x going to the right, and this point is A, and we have point B at the support, then the rotation at B relative to A is equal to the area under the curvature diagram. So the integral of the curvature with respect to x from x equals 0 to L in this case. So if we draw the bending moment diagram, it'll be parabolic and look something like this. And we know that by cutting the beam, you get an equation for the bending moment as minus wx squared on 2. And dividing this by EI gives the curvature. So therefore we're integrating minus wx squared on 2EI over x from x equals 0 to x equals L. And taking the constants outside the integral, so minus w on 2EI, and integrating x squared, we get x cubed on 3, evaluated from x equals 0 to L, so that gives minus wx cubed on 6EI. And you can visualize theta b relative to A as the integral over theta, evaluated from theta A to theta b. So that'll give theta b minus theta A. And we know the rotation at B is 0 for a cantilever. So what you get is minus theta A on the left hand side. And the negatives cancel to give you a positive rotation, which is anti-clockwise at the tip of the cantilever. And that's the maximum rotation. Now to obtain the maximum deflection, we want the distance between the tangent at A and the tangent at B. So we're looking for the tangent at A relative to B, which is this distance over here, is equal to the integral of x by m on EI, which is the curvature. So that was minus wx squared on 2EI. And we integrate over x from x equals 0 to x equals L. So taking the constants outside the integral, we have minus w on 2EI. And then we're left with x cubed, which evaluates to x to the 4 on 4, evaluated from x equals 0 to L. And therefore we get minus WL to the 4 on 8EI. And this here is the maximum deflection for the cantilever. Alternatively, you can use the centroid definition to find the distance between the tangents, which is x bar by the integral of the curvature over x from x equals 0 to L. And we know that the centroid of the curvature diagram is at 3/4 of the length of the beam. So therefore we have 3/4 L, and that's multiplied by this integral, which we already evaluated, which was theta b relative to A of minus WL cubed on 6EI. So doing the algebra will give you the same result. Let's find the maximum deflection and rotation for this simply supported beam using the moment area method. And we know for this simply supported beam, the bending moment diagram is piecewise linear. It has a magnitude of PL on 4 in the middle, and dividing through by EI gives the curvature diagram. Now if we designate this point A and this point B, then theta B relative to A can be obtained by integrating the curvature, which is m on EI, over x, and in this case we integrate from x equals 0 to x equals L on 2. And given that the curvature diagram is linear, we can obtain the area by simple geometry. So given this distance here is L on 2, the area is 1/2 by the base of the triangle by the height of the triangle. So that gives PL squared on 16 EI. And as we know, that's theta B minus theta A. And we know that by symmetry of the beam, the slope of the tangent to the curve is 0 at B, and the slope of the tangent to the curve at A is negative. So that means if this is 0, then this equation here gives theta A is minus PL squared on 16 EI. And as expected, theta is clockwise at A. Now because the curvature diagram has a linear geometry, we can find the tangent at A relative to B using the centroid definition and multiply by the integral of the curvature over x from x equals 0 to x equals L on 2. So that gives the distance between a tangent at B and a tangent at A at A. So that will be tangent at A relative to B. And we can see that that's going to give us the maximum deflection. Now the centroid of a triangular area is at 2/3 of the length of the triangle, so that will be equal to 2/3 by L on 2, being the length of the triangle. And we multiply this by the integral, which is the area in the triangle, and we evaluated this already. So that will be PL squared on 16 EI. And if we cancel out the 2's, we see that the maximum deflection has a magnitude of PL cubed on 48 EI. And note that this distance between the tangents is below the beam, so we can just put a negative sign here. Find the deflection at the tip of this beam, which has an overhang. So by intuition, the deflected shape would look something like this. And let's draw the bending moment diagram over here. So if you cut the beam from right to left, you're going to get P times L, which is the force by the moment arm, which is a negative bending moment at the support, on EI gives the curvature diagram. And at a pin, the bending moment is 0, so this bending moment reduces linearly to 0 as follows. So here we'll take point A, B and C as follows. So we have a tangent at A tangent at B that looks something like this, and a tangent at C that's more steep. So if we extend the tangent at B as follows, it looks something like this. So this distance is the tangent at A relative to B, and this distance here is the tangent at C relative to B. And by similar triangles, this triangle here has a length 3L, and this triangle here has a length of L. So by similar triangles, this distance here is a tangent at A relative to B on 3. And therefore the tip deflection is equal to the tangent at A relative to B on 3 plus the tangent at C relative to B. And because the curvature diagram is piecewise linear, we can use a geometric definition of the tangent. So for example, the tangent at A relative to B is equal to the centroid by the integral from xa to xb of the curvature m on EI with respect to x. So if we take our origin on the left, then the centroid of this triangle is at 2/3 by 3l. And the area under the curvature diagram is obtained using geometry. So we have x bar multiplied by half the base, which is 1/2 by 3l by the height of this triangle, which is minus PL on EI. So that gives minus 3PL cubed on EI. And the tangent at C relative to B can be obtained in a similar way. So if we take our origin on the right, the centroid of the curvature diagram is at 2/3 L. So we have 2/3 L by the area under the curvature diagram, which is 1/2 by the base by the height. So that gives minus PL cubed on 3EI. And now if we substitute these in this expression, so the tangent at A relative to B on 3 is minus PL cubed on EI, and then plus the tangent at C relative to B, which is minus PL cubed on 3EI. And this here is the same thing as 3 on 3. So the deflection at the tip is minus 4 PL cubed on 3EI. Recall the moment curvature relationship, which we differentiate to get the shear force, and differentiate again, which gives dv dx. So the fourth derivative of the deflection with respect to x gives the negative of the uniformly distributed load. Now if we integrate this expression, we get the integral form of the shear force, which is basically integrating the uniformly distributed load with respect to x. And then integrating this equation again gives the bending moment. And we call these the equations for our conjugate beam. Now if we write the curvature as the first derivative of the rotation with respect to x, then that gives d theta dx is m on EI, and then separating the variables and integrating this expression gives an equation for theta as the integral of the curvature with respect to x, and integrating the rotation gives the deflection. So these are our equations for the real beam. So effectively the integrals for the conjugate beam and real beam are equivalent, except you have the uniformly distributed load in the conjugate beam expression and the curvature in the real beam expression. So if we can construct a conjugate beam with the same boundary conditions as the real beam, then the shear force in the conjugate beam becomes equivalent to the rotation in the real beam, and we can thereby do statics on a conjugate beam to obtain a shear force, and that's equivalent to the rotation. And this is best illustrated with an example. So given our cantilever subjected to a point load, it has a linear bending moment diagram of minus PL at the support, and dividing through by EI gives the curvature. So this is our real beam. And now to construct our conjugate beam, we need to match the boundary conditions of the real beam. So designating these points as A and B, we know the rotation at A, being a free end, is not 0, and the deflection at A is also not 0. But on the other side, the rotation at B is 0, and the deflection at B is also 0 at a fixed support. And the shear force in the conjugate beam is equivalent to the rotation in a real beam. So that means the shear force at A is not equal to 0, and the bending moment in the conjugate beam is equivalent to the deflection in the real beam. So therefore, in the conjugate beam, the bending moment at A must not be 0. And on the other side, theta B is 0 in the real beam, so the shear force at B is 0 in the conjugate beam, and the deflection at B is 0 in the real beam, so the bending moment at B is 0 in the conjugate beam. So the support that mimics a non-zero shear force and non-zero bending moment is a fixed support. And on the other side, a free end has 0 bending moment and 0 shear force. So these are the boundary conditions for our conjugate beam. And finally, we need to load our conjugate beam with the curvature from the real beam. So therefore minus W must be equal to the curvature, and the curvature distribution is linear, and minus PL on EI at the support. So therefore W is PL on EI, and when we get a positive W, the load acts downwards. So effectively, applying our curvature from the real beam as a load on the conjugate beam, we get the following result. And this has a magnitude of PL on EI. And now we can apply simple statics by cutting this beam on the left infinitely close to the support, thereby exposing a shear force and bending moment. And we take the left-hand sign convention, and the resultant acting on this beam, which we'll call FR, is equal to 1/2 by the base of the triangle by the height. So that gives PL squared on 2EI. And by statics, this force resultant is equal to the shear force. And the shear force in the conjugate beam is equivalent to the rotation in the real beam. So therefore, our rotation is PL squared on 2EI, which is well known for a cantilever. And now taking a sum of moments about the support, we get minus M minus the force resultant by the moment arm, which is 2/3 L, and that's equal to 0. So therefore the bending moment is equal to minus the force resultant, which we calculated as PL squared on 2EI, multiplied by the moment arm. So that gives minus PL cubed on 3EI. And as we said, the deflection in the real beam is equivalent to the bending moment in the conjugate beam. So that's our deflection of the cantilever. And as we can see by the deflected shape, the rotation that we obtained is positive, meaning it's anti-clockwise, and the deflection is acting downwards. So we got a negative result.